Hi. In this video, we will present rule of probability number 5. Toward that end, I'm going to open a whiteboard to share with you. And I'm going to look at the notes from last time and add one more note for rule number 5. The rule called the conditional rule of probability. Conditional, as opposed to the marginal rule of probability. So the conditional rule of probability states the following. It states that when you're interested in calculating the probability of an outcome, given information that is known prior to that outcome's occurrence, we usually use a shorthand notation where we separate A by a vertical line from B, in which A is the object of the probability, the object of our uncertainty, and B is the condition or the restriction or what is known or given about the context in which we are calculating a probability. So a conditional rule of probability allows you to compute probabilities not in a vacuum, but rather in a specific context. For example, we can calculate the probability that someone may be detected as infected with COVID-19 in general. So that would be one kind of a probability that we could calculate. That would be under Rule 4, the marginal rule of probability. Now, if we're talking about a person who lives in an island that is in the southern hemisphere in the Atlantic between the continent of Africa and the continent of South America, given that a person is living in an isolated island between Africa and South America, if we ask what is the probability of becoming infected by COVID-19, the answer is not going to be numerically the same as the answer of what is the probability that a person is infected with COVID-19. That's because the applicable laws of large numbers are going to give us different probability spaces. In one probability space, we're not imposing any restrictions, so we're talking about the probability of becoming infected in the presence of trillions of agents, infectious RNA structures of COVID-19, not DNA, but RNA structure of COVID-19, and in the presence of 7.5 billion people. Whereas in the other probability, in the constrained or conditional one, we're looking at a person who probably does not come into contact with a lot of the pathogen or a lot of other human beings who've been infected. And as such, that person would probably have a lower conditional probability of infection than a person who is the usual or generic person in the world. So in some situations, the probability of A given B, in all situations, the way that you calculate that is you would count the number of ways in which A would happen within situations of type B, and then you would divide that by the number of situations of B. Not of the entire probability space, but only of the given portion of the probability space. The result could be that the probability of A conditional on B is equal to just the probability of A overall. In this case, what we say is A and B are independent outcomes. So that's an important way of identifying how two things may be unrelated. And it could be the case that the opposite is true, that the probability of A given B is not or are not equal to one another. And when they are not equal to one another, we say that A and B are so-called dependent outcomes. So the conditional rule of probability serves a very, very important task, a very important role in uncertainties. It helps us identify when things may or may not be related to one another in an uncertain environment. So when people ask, for example, should we be wearing a mask to prevent the transmission or the infection or the reinfection of COVID-19 as an agent? And the answer would be, well, it depends. We might use a mask when we are within 6 feet of another human being whom we are not sure may or may not be infected. That may help lower the probability of infection, because given that we have a cover, the RNA strands may not, the coronavirus strands may not permeate the mask and thus allow us to remain safe. And so depending on whether we're wearing masks or not wearing masks, depending on whether or not we wash our hands a lot or not, depending on whether or not we maintain a safe 2 meter, i.e. 6 foot distance from people whom we are interacting with on a very infrequent basis, depending on those 3 factors, the probability of infection may be low if we do the right things, or may be higher if we don't do the right things. Now, those are the kinds of principles that we've developed over the centuries as we have learned to deal with pandemics. In the first pandemic that I studied, which would be the Black Plague in medieval times that I read about, you have a situation where almost 15% of Western population died in that situation. In the pandemic that we call the Spanish flu of 1919 to 1920, we had 50 to 60 million people who, somewhere in that range, who died, which constituted about 8% of the European population at the time. And now we're talking about, about a few 100,000 people dying in a world of 7 billion. So we have used the conditional rule of probability to learn about practices that help us survive a pandemic in which we don't have a vaccine or a means of developing immunity before the virus becomes broad-based and becomes available all over the place. So I hope that the conditional rule of probability computation, and I hope that the conditional rule of probability is something we, that you find useful, that this conversation about the conditional rule of probability is found useful. Thank you for watching this video. I'm going to stop the recording and create 2 more recordings, one for the addition rule and one for the multiplication rule. Thank you.